All right. So today I'm going to be going over a little R project that I did where I looked at the New York City.data.gov, one of their data sets, specifically looking at car accidents. I extracted the data to only show 5 cars in one accident. So only instances of 5 car accidents, basically. How did I do this? I went to the New York City Open Data website, and I filtered the data to basically the contributing factor of vehicle 5 to not blink. And also the contributing factor of vehicle 5 is not unspecified. Those two observations to me indicated that there was no vehicle 5 in the accident. You can review the data set itself and check into that and look at my reasoning why. But essentially, I wanted a smaller data set that I can hone in on 5 car accidents because they're unique in that if there's 1 or 2 or 3 car accident, it could have just been someone running a red light. But if you have a 5 car accident, it was probably icy or someone was really going quickly. And I really just wanted to look into that and see some key facts about, 5 car accidents in New York City. So what we got from that extraction there's a few little things I wanted to go over. Essentially, the population size, almost 2 million. There's 443 in the sample, 29 variables total. And surprisingly, there were no deaths in 5 car accidents in New York City for the entirety of the data set. And the data set is from 2012 and onward up till 4/7/22. So not too many days ago, exactly a month ago, actually. So that was the last 5 car accident in New York. So I wanted to break down this data into some components, just see everything, form a few predictive models, et cetera, et cetera. I really wanted to figure out the who, what, when, where, and why of 5 car accidents in New York City. So where are they occurring? Who, under which circumstances are getting in these accidents? What kind of cars are wrecking the most? And those two I kind of visualized in 2 different ways. And I used some new packages that I hadn't used before to do that. And also which season? Are there more people in the summer wrecking when they're partying and then driving in? Or is it more people in the winter sliding, just crashing, and then, the domino effect to get those 5 car accidents? So why are crashes happening the way they are? I wanted to form a predictive model and see if everything's significant and just really go down that path and just see what makes the data the data. I have a few hypotheses here that you can read over if you'd like, but essentially, I'm just going to get into it. I do have RStudio Cloud open. I just prefer to use it personally. I think it's a lot easier. There's a lot of issues of using RStudio on the newest version of Mac, and you avoid them all if you use RStudio Cloud. So without further ado, this is really what I did, step by step. Going into the files, I uploaded the file here, project dataset. You can click on it, whatever, but I just wrote this down. Essentially, we're using the tidyverse, and then we're using readx1 as our first library. So we're mapping this document to Z throughout the rest of the script file. I think it's just easier to use. I don't think I'd use Z for anything else. It's just, for me, it's the equivalent of DF. It's just a little personal preference that I have. But anyway, just visualizing it. We got right here, boom, boom, boom. You can't see the whole thing. That's kind of why I wanted to show it in Excel. But this is essentially what it looks like a little bit further on after it's been cleaned a little bit. Going down the list, we have average latitude and average longitude. Why am I using these to impute latitude and longitude for everything where there's NAs in there? So you can't use NAs in predictive models. It's really difficult to use like ggplot2 if you have NAs in the data set because it'll spit out some error. So to get rid of them, I imputed them with the average for both of these. And really that doesn't hurt the data set itself because it is normally distributed, as you will see here. I would not completely, but I would ignore the highest peak because that's what we imputed. We added values to this column that were not there before. So this specific column isn't as reliable as the other ones. However, you can see normal distributions, a rightward skew in terms of latitude, meaning more accidents happen to the east in New York, but they're generally in the center. So they're in the center east part of New York. And it's also kind of interesting to see the longitude. They happen in the south of New York too. So this is, longitude, the highest being north, the lowest being south. Most of them do occur kind of in that lower Manhattan area. This actually comes out to, when you look at, I don't know, Google Map, the imputed value shows, where is this? Boom. It is New York City Hall. That is the value that I imputed. Kind of interesting that these accidents all, if you took the average of the latitude and longitude, equals New York City Hall. But it is what it is. It's some coincidence. Maybe they put it there for a reason, right? Central access to all the movements going through New York, essentially. That's really what that shows. Going down, I also imputed a lot of the NAs throughout the data set. Anything like the zip code, I imputed to 0 because if you impute it to the average zip code, that might not really make sense because zip codes, I don't really know the way that they're structured, but they're not based around latitude and longitude, to my knowledge. So if you put it as the average zip code, it might mess up the data. So put it at 0. We don't need to see it anyway. It's not something that we really go into. But I just wanted to keep a clean data set. That's really one of the central goals of this project, is to clean this giant data set, make it usable in a few ways. All the text columns that refer to street names, I would change the street names that were NA to unspecified. Could have done it this way as a function, but kind of figure that out after the fact. It is what it is. And then kind of going down, basically, I wanted to put everything in proper case. So this is the original data set. You can see there's a lot of text as all capitals. There's some that is in proper case. There's some where it's all lowercase. I wanted everything to look like it had each word in it has the first letter capitalized. I feel like it makes it look more consistent, more clean. So that's what I did. And that was done through stringr, which is a library I haven't really used before. It was basically using the string to title function, which puts everything into proper case, right? Finally, we have, well, not finally, we're only 1/5 of the way through. We have a new library as well. For me, it's called Luberdate. Essentially what it does is I was able to break down the date that when the data set first comes in, this data type is actually not a date. So let's see. Its data type is actually a double instead of a date. So how do we get this crash date to equal, the month, so that I can then break it down into summer months and winter months to actually look at? Use this Luberdate package. You set up the data, you look at it. It's essentially year first, month, and date, and it's separated with dashes instead of slashes. So from there, I was able to map these new columns out. Summer is essentially everything that is not in the summer equals 0. Everything that is a 1. Same thing for winter, and that's its own column as well. Then we go down here. We're looking at the winter table itself. Now, why did I do this? I wanted to count the instances of each, kind of like a little transformation, right? So if we there were 320 counts of non-winter, there were 123 counts of winter in the data set. Considering there's 4 seasons, that's pretty significant. We're looking at summer. It's also pretty significant, but it's a little bit less. So I wanted to see what that difference actually entailed. It's actually 28. And then if you look at the percentage difference between the two, winter has 22%, 23% more accidents than summer. So you can pretty much see right there that even in these pie charts, that there is a little bit of a difference between the two. I don't want to go crazy with these pie charts, but you can just kind of see this is about a third. This is less than a quarter. So I guess we really see that in New York City, one of our central questions, a lot more accidents do happen in the winter than the summer or any other season really. Now I want to visualize this using a few libraries down here and also really manipulate the data. So this was a little project that I had never done before. It was mainly to take vehicle type code 1, right? So we go all the way over here. We have vehicle type code 1, 2, 3, 4, 5. It shows which vehicles got in an accident. So it's safe to say that each of these represents another vehicle, right? So for the data set, there's actually 5 times more vehicles than observations. So there's about 2,000 vehicles in total, whereas our data set is, 450. So how do we get this to actually be its own little table? Did it in a few ways using, deployer, probably butchered that, but I essentially created a data frame from each table that's coming from these columns. So like I showed you earlier with these tables, it basically counts each instance easily so that you're able to, instead of moving over observations, you just move over the count of those observations. So we take that, we rename it into A, just so it's easier to, we'll show you later, but just append it into a larger table. And, rename frequency to frequency 1, which when we merge everything into a table, we're going to have frequency 1, frequency 2, up to 5. And it'll make it really easy to really get the total from that, just add up each column and then it's easy. There's probably a library for it, but I don't really know what it would be called. So this is my own little way to get a bunch of different categorical variables and then get the count of each. So really merging all the columns in, right? So now we have, and I'll just kind of show you. So we have A. What is A? So A is the first count of vehicle type code 1. This is showing, the frequency of which cars were in accidents. B is different because it's a different column. There was a lot of similarities, but this is actually different from what we just saw. So essentially what I'm trying to do is to merge all these together into one common vehicle type column, right? So initially, this would just show frequency 1, frequency 2, up to 5. But rather than rerun it, deal with all that, it's basically what I'm doing is taking the total of these into this real frequency column. So essentially, A, B, C, D, E, the counts of those equal the real frequency. So these passenger vehicles, suppose there's 105 data sets, this would equal 500. Going down that list, we have a few columns that we wanted to drop, frequency 1 up to frequency 5, since we don't need them. We only need the real frequency column. And then going down, I wanted to convert it into an integer. And then I wanted to show the type of real frequency to make sure that was an integer, because originally it was set as a double, which was kind of messing me up. I don't know why it was, but I guess that's just a default setting in R. But we are going here. This puts this into proper case, like I showed you earlier, where it's the first letters capitalized and so on. And there you go. So vehicle type is essentially the table that you get when you go through that whole list. You mess with it. Excuse me. There's a few duplicates, but I don't really want to worry about it. I just wanted to kind of visualize what the top 3 were, because I don't have access to if there was a different criteria, right? So I don't know if taxi capitalized and taxi whatever, one had to do with an Uber or the other. I just wanted to keep it as it was so that I'm not skewing the data in a way that it doesn't need to be skewed. But I wanted to see the top 3, right? So the top 3 of these categories. So what it came down to was I put it into this new library. I forget which library this was specifically, but what this is showing is the real frequency of the top 3, something that I haven't really done before. And then I did want to visualize it as well using ggplot too. So going down the list, what did I really do with this? Start it up. I want to reorder the data set, sort it by real frequency descending. So this is the frequency of accidents versus the type of vehicle itself. Kind of cleaned it up a lot. I set it as a rainbow just so you can really see the differentiation between the two, because a sedan and a passenger vehicle kind of on different sides of the spectrum. A station wagon and a sport utility vehicle, I don't really necessarily know what that even is. But it kind of makes sense just because the amount of sedans in New York City is probably huge. So it's the most frequent car, which also leads to the most frequent amount of car accidents. Something that I thought was interesting is I had originally hypothesized that it would be taxis. Obviously wasn't, because when you're in New York, drivers are crazy in taxis, but it's not so. I guess those medallions are really expensive and they don't want to wreck their ride. But going down the list of how I did it, basic ggplot syntax, you just take a bunch of different components, map it to one variable, call a variable at the end. So it's a geometric bar chart, the title, the subtitle, some labels in there. I wanted to add the classic theme. If you don't have the classic theme, there's little grid lines that I thought looked weird, so I took them out. And then also to center the titles. So that's essentially the main thing, like what types of vehicles are causing these accidents. A lot of sedans, a lot of, family vehicles, essentially, and not sports cars or motorcycles, which I thought is good because, if a motorcycle is in a 5-car accident, probably wouldn't be doing so well. And that probably has to do with there being no deaths from 5-car accidents in New York City since 2012. All right, now we get to the nitty gritty. I wanted to formulate a model based around a few attributes, right? So we had summer, winter, latitude, longitude. I thought it'd be interesting to look at. And as it turns out, none of these variables were significant. The R squared was ridiculously low. It's just not a worthwhile model. This was initially what I wanted to look at, though. So it's unfortunate, but it is part of life. However, when we reduce latitude and longitude, the y-intercept is accurate. Now, I don't know what logic really would explain that, but I don't know. I guess there is some merit to using winter and summer in predictions, but it's not great and it doesn't really make sense to use. So switching gears, because that obviously did not work out the way that I wanted it to. We really have, I tried out a new library that I've worked with a little bit in the past. Basically, I wanted to dummy code each contributing factor, right? So if we go back to contributing factors, there's a whole lot. If I was to dummy code each of these columns, it would be taking a long amount of time and it would use more RAM than I have on RStudio Cloud. So to avoid that, I only use the first contributing factor. So we're only looking at the first vehicle in the crash. I don't know if this is the vehicle that starts the crash or the last vehicle to get tied into the crash, or if it doesn't matter, if it's just whoever gives their statement to the police first. But essentially, I wanted to map it out to where other vehicular is its own column that is coded to 0 or 1, 1 being the existence, 0 being that variable didn't happen, and just build a predictive model based on that, just these little attributes, right? So this would kind of see if someone is drunk, will this lead to a 5-car accident? And that type of deal, like which variables contribute the most to 5-car accidents. So going down the list, we have a whole lot. I initially had, I think it's 28 variables in here. And it's a lot more significant than the other one, but there is a lot of wasted space that just doesn't really matter, right? 1 second. Essentially, what you're seeing is a model where there's only one significant variable, unsafe speed, right? So if drivers are driving at an unsafe speed, that could lead to a 5-car accident. Not very insightful. Just going off the residuals, it's not a very good model. Going down the list, I did kind of want to demonstrate a few other things. This model is after 2 iterations of trimming the weakest variables. The only significant thing really, you have what? Driver inattention and distraction is the only somewhat significant little attribute at the 0.1 level of significance, which, correct me if I'm wrong, it might be 68% likelihood versus 95% is what you really want to see. And the intercept is significant here. So I wanted to show a little plot of the residuals kind of as a final touch. What this is really showing, these residuals, is it's comparing the fitted model, which is in red, to the actual observations. Not a lot of fit there, right? Very low R squared, and it's not really showing a whole lot. All right, so it was supposed to show another one, but I'll just show you in here. Essentially, you have the standardized residuals and the residuals, right? So standardized residuals attempts to take the square root of everything. So it's not showing such a crazy dispersion. But essentially what you should glean from these graphs is if it was a great model, you'd see them all along the red line. They are not, therefore it's a pretty bad model. So I would probably use something else in the future instead of really just showing, you know, all these variables, right? But to break it down really, I guess the last model that we had, you know, 6% R squared, that's essentially 6% of the observations really fit the model. The correlation coefficient, essentially, X equals Y 6% of the time. And adjusted R squared is even less just because nothing's really significant. It's actually negative, which I've never seen before. So I guess in conclusion, going back to these central questions, what makes up the who, what, when, where, and why of the New York City 5-car accident data set? You know, where are the accidents happening? Center of New York. Who's crashing? A lot of sedans, probably a lot of families, to be honest. Not a lot of taxis, surprisingly. So that really addresses the what kind of cars. When, a lot more in winter than summer. And then why are crashes happening? A whole lot of reasons, but I guess the first one that sticks out is really having to do with unsafe speeds. So the moral of the story is, if you're in New York City, you don't want to get in a 5-car accident, drive at a safe speed. And that's really all that there is about this. So thank you.